Yes.
Okay, so I start now. Thank you very much for the invitation to this workshop, which has been very exciting and inspiring so far. And thanks also for being here at this, what in Lancaster seems like the midnight hour. I talk about curiosity and learning in infancy. So my title is slightly changed because yesterday I thought, is curiosity really a driver of learning in infancy? And this is really everything I want to talk about. So I just want to give an overview of the studies we have done to ask different questions about curiosity. And as Mia said, my focus is on, Sia said, my focus is on infancy. So really on the first 1-2 years of life. I don't need to preach to the converted here, saying that infants are already active learners and explore their world actively through intrinsically motivated information seeking. And this is my concept of curiosity, is mainly focused on what it means for information seeking in the first 2 years of life. So these are some questions we can ask about infants' active learning, and there are many more, but these are 4 questions I want to talk about: how they explore the environment. Do they even explore the environment systematically or maybe randomly? How does curiosity affect learning? How can we measure curiosity in infants? That's not an easy question to answer. And then finally, and I think I'll probably devote most of my talk to that part, what are the mechanisms driving curiosity, exploration, and information seeking in infancy? So it may be worth to briefly recapitulate a bit of history of curiosity. Berline in the 1950s and 60s was of course, a pioneer in this research, and he developed a useful taxonomy distinguishing between what we call diversive curiosity, which is basically avoiding being bored, seeking stimulation to accumulate information, and specific curiosity to fill a knowledge gap, in a sense, for a particular bit of information. And although these 2 notions are sometimes a bit, when maybe not distinguished clearly enough, the assumption was that they have, in fact, qualitatively different processes underlying them. And there are other taxonomies, like the interest deprivation taxonomy by Littman and colleagues, and several others. But I find this one between diversive and specific curiosity particularly useful. And also, I think it's worth to briefly reconsider what explanations have been given for the origins of curiosity. So one idea is that it's a drive, like hunger or thirst, so the drive to acquire knowledge, basically. The second one is a desire to reach congruity, so that the system gets out of balance if current knowledge and current experience differ. So it's closely linked to the prediction error idea of curiosity, so to avoid uncertainty. The third one, which is a bit related to this predictive one, is the one of the information gap, the knowledge gap, to look for a specific, to recognize that there's a gap in one's knowledge about something specific and trying to close this gap, maybe like a scientist or through directed search, looking something up on Wikipedia or so. And finally, the learning maximization approach, the idea that learning itself is a pleasurable, a rewarding event, and therefore we pursue learning for its own sake. Theoretically, I mean, they all overlap a bit, but I think it helps to think of them as different explanations when you want to really develop a theory of curious learning. So let's first talk about the study where we looked at how infants explore the environment. Do they do so systematically? So the question, how do infants select information when they explore? There has been some work on this when infants are exposed to information, in a sense more passively, that they prefer intermediate levels of complexity. Sorry, like the Goldilocks effect, that the paper that LiCiD and colleagues published in 2012 for visual complexity, in 2014 for auditory complexity. So here is the graph from their visual complexity study, that infants looked at sequences of shapes that were more or less predictable in which shape would come next. And they found that infants looked away less for sequences of intermediate predictability, intermediate complexity. And of course, the Goldilocks effect, this idea of the intermediate level of complexity being special, has a long history. Donald Hebb already talked about this, Kagan, Löwenstein, and of course it links closely as well to Vygotsky's zone of proximal development. The kind of intermediate novelty is best to learn. So these studies, the Goldilocks studies, were receptive infants sitting at a screen and looking at sequences presented to them. We asked the question, what about infants generating sequences of exploration actively? So what we did was we 3D printed sequences of shapes that, in a sense, morphed from one shape into another, more or less gradually. You see, from a round ball into a cube, or decreasing the number of corners in the yellow ones. And that means that these objects have a defined similarity relationship to each other within one color sequence. So this is work I did with Katie Toomey and Kehan. So the question was, when you give these sequences to infants, in what sequence do they explore them? Do they touch them? Do they investigate them? And does that change with age? So when we look at a sequence like the yellow one here, so if we start with the leftmost one, we can quantify the perceptual distance to the next one is step 1, then step 2, step 3, and step 4. So we can, for 2 objects touched in sequence, we can say what kind of distance lies between these 2 sequentially touched objects. And what we did was to give an infant one of these, and then to explore for 15 seconds as a prime object, and then give them the other 4 and see in which sequence do they explore the other 4. And we did this with 12, 18, and 24 months olds. So let's see if this video works. You might have seen this already in the head-mounted eye tracking workshop. So here he gets the prime object. And is unreasonably excited about this little pyramid. And then he's presented with the remaining 4, of course, in random order that was all counterbalanced. And then we investigated in which order would the children then touch the remaining objects. Okay. So, and this is what we found when we looked at which object did they touch first. Here, the orange one is the most similar one to the prime object. The yellow one is the most dissimilar one. We find that they do touch them systematically across all ages. They preferentially touch either the most similar or the most different item in the sequence. And as I said, across all the ages. So they don't explore randomly. They preferentially go for the most similar or for the most different to what they had seen to the prime object. And then we, that looks a bit messy, sorry. Then we characterize the sequences of objects, how they touch them. So here each rectangle is one object touched, and the colors indicate the similarity to the previous object. So for example, the top orange here indicates one similarity step away from the prime object, and then the white one after they're touching the same one again. And we can see the sequences across the 3 age groups. What we did was then to cluster them to see, are there any similarity clusters that we can distinguish different types of exploration in these age groups. And in each age group, 2 clusters came out as the optimal clustering. In the first one, for the 12-month-olds, the clusters were determined by the mean similarity between the objects touched. So you see, for example, here in the second cluster, blue dominates. So they were going more for dissimilar objects, and in this larger cluster, it's orange dominates. So they were going more for similar objects. In the 18-month-olds, the clusters were determined also by the mean similarity. but also by the touch sequences. So some children generated longer sequences and others shorter ones. And in the older age group, again, how many objects were touched, the length of the sequence, and the variability in the sequence. So, for example, here they would always go for the next one, like many oranges in a row, and here they varied the similarity between successive objects. Now, each infant contributed to trials, and it would be nice to say that these are individual differences between infants. Some are more similarity-oriented, some are more dissimilarity-oriented. However, unfortunately, they didn't consistently fall into each type. So an infant was just as likely to contribute 2 sequences to type 1 as one to type 1 and type 2, for example. So these don't show individual differences between infants, but between individual exploration sequences. So, but what we can conclude from this is that infants do show systematic patterns in pre-exploration, that the first touch is usually to the most novel or to the most similar object to the one that they had previously seen, and that the exploration patterns differ between length and distance between successive objects that the infants generate. Coming back to the Goldilocks effect, overall these sequences were of intermediate complexity, but not item by item. So sometimes, of course, infants would choose the most similar item. Sometimes they would choose the most different one, sometimes an intermediate one. But on average, these sequences were of intermediate complexity. So there were very few sequences where infants would always go for the next similar item. So much for this study. And then in another study, we asked, how does curiosity affect learning? And one way to look at this was with using ERP, investigating the brain basis of the Goldilocks effect. So the question, does this the preference for intermediate complexity that infants display, does it also show up in the ERP? What are the underlying brain processes? That's the study I did with Sylvie Leonard. So what we did here was we had a sequence of 19 morphed images of these animals. So we started from the two extremes and then morphed one into the other. So again, on each step, there's a clearly defined similarity relationship to the previous one. So if we have a sequence of these 19 animals here, and we present sequences of these to the infant one by one. So for example, if you start with this one, and then we go 4 steps to show this one, we might then go 1 step to that one, 7 steps to this one, then again 1, 4, and 7. So you get the idea. We can present a sequence of these objects to the infants, and each 2 successive items either have a distance of 1, a low distance, high similarity, a distance of 4, medium distance, or a distance of 7, where they're very different, very novel. We did this study with 9-month-olds, and we measured the ERP to the presentation of each stimulus. And then we compared the ERP response to the small distance steps, the medium distance steps, and the large distance steps. What we found in the occipital areas, in the early visual ERPs, here around 100 milliseconds, that the ERP differed between the small distance, the blue line here, and the red and the black, the medium and the large distance. But the medium and large distance ERP did not differ from each other. So early on, the ERP reflects a similar to not similar difference, which is perhaps unsurprising in early perceptual processes, a similarity judgment or similarity response in the ERP. But looking at frontal central areas a bit later, 300 to 400 milliseconds, we now find that the ERP is different for the medium distance one, is different from the small and large distance one, and quite strongly so. So the ERP for the small and large didn't differ in this interval, but they were different from the ERP for the medium distance. And this location and interval is the PB component that hasn't been studied a lot in infant ERP, but it's linked to expectation and to stimulus relevance has been argued so far. So we find that this PP component is in a sense a neural indicator, an ERP indicator of the preferential processing of intermediate novelty in this time interval. So early perceptual components reflect stimulus similarity. Later components reflect the special status for intermediate novelty that we also found in the behavioral Goldilocks studies. So this might reflect a propensity to learn preferentially from intermediate novelty. So linking the preference with learning. But staying with learning, we can ask how does curiosity affect learning? How do we learn when we are curious is the question here in another study with my PhD student Torian Chen. So when we are curious about something, do we learn better only about the object that we are curious about? So is the curiosity focused to the object of our curiosity? Like in a knowledge gap, we have a specific question that we want to close. That's what we are curious about. Or being in a state of curiosity, does that enable broader learning more generally? So that was the question we asked here. So how do we make people curious in studies? Well, in adult studies, there are mainly two ways. One is to ask trivia questions. We've heard a few examples of that already in the workshop, like what is the name of the composer who wrote Don Giovanni? And then we can ask people, how curious, do you know the answer? How curious are you about it, etc. Another one is to present people with blurred images. There have been a few studies using that, especially when the images are blurred to an intermediate degree. And in a study by Jetma, for example, they reported, and others as well, that they report consistently that adults consistently self-report high curiosity when they watch these blurred images. Now, infants, of course, we cannot ask them trivia questions, so we use blurred images. But looking briefly at work with adults on this question, does curiosity enhance learning more broadly, or is it specific to the object of curiosity? That's work by Matthias Gruber and colleagues. And so they use trivia questions. So they asked, what does the term dinosaur actually mean, for example? Then a face occurred, and then they were given the answer to the trivia question. And they were also asked, how curious are you about this question? And they found that in adults, when they were more curious about the question, they could afterwards remember the faces better. This incidental information that had nothing to do with the object of curiosity. Although I should say in Gruber's study, they asked how likely would this person be to help you answer the question. So it was kind of linked to the trivia question itself. But they found that recognition for faces was higher when adults were curious. When they did a similar study with 10-year-olds, children and adolescents, they didn't find this effect, though, that there was no enhancement of memory for incidental information when they were curious compared with when they were not. So we wanted to answer this question with infants, with 8-month-olds, and here's what we did. So we put infants in a curious state by showing them a blurred picture on a screen, and then an unrelated object, and then the resolution of a blurred picture. And then we showed them a clear picture, so they weren't curious, another incidental object, and the clear picture again. Counterbalanced, of course, whether we showed the curious or the non-curious sequence first. And then we had a preferential looking phase where they saw both of these incidental objects next to each other. And the idea was, if the effect of curiosity is broad, like if this blurred image induces a general state of better learning, then they should learn this incidental object better than this one here, where they weren't curious. And at test, they should then show a novelty preference for this object, because they had encoded that one better. Right? But if curiosity is not broad, if they were not more curious, didn't learn this incidental object better than that, there should be no preference in looking. So what we found is during training, they looked equally long at both incidental objects following the first object. But at test, they showed a clear preference for for the incidental object that had occurred in a non-curious state. So from that, we conclude that curiosity in infants, like inducing curiosity through a blurred image, leads to better general learning, also about objects that occur that occur after this object, but have nothing to do with it. So there's in infants, curiosity-based learning is more general, unlike in teenagers, but like in adults. So there seems to be kind of a U-shaped developmental curve. And then we thought, what could be an explanation for this? So infants and adults learn broadly when they are curious, but older children, adolescents do not. They only learn better what they're curious about. So a possible explanation is that with age, curiosity becomes more focused from a broad exploration to a more focused knowledge gap type. Whereas at the same developmental time course, working memory capacity increases or general processing capacity increases. So it's possible that adolescents, teenagers are at this point where curiosity has already focused, but working memory general processing capacity hasn't increased enough to nevertheless encode the incidental information. So that's one possibility to account for this U-shaped developmental process. But how can, so here we assume that infants are curious when they see blurred images because it's been shown consistently with adults. How can we measure curiosity in infants though? For adults, older children, there are questionnaires. And so we are developing a questionnaire currently as well to measure trait curiosity in infants. So it's a parent report questionnaire, of course. And the idea is to create a new general measure of curious behavior in infants. Also, of course, to be able to study individual differences. So we've just started developing this. I just want to mention it here because it might be useful once we are done. So there are 36 questions with a target age range of 5 to 24 months. For example, my child shows visible enjoyment, for example, smiling, gurgling, babbling when discovering something new. My child actively inspects a variety of objects, whether it be toys or ordinary household items. My child starts playing on their own rather than waiting to be given something to play with, and so on. And then we also have one question about, I would generally describe my child as curious. We've just piloted this now with 22 infants with a mean age around 10, 11 months. Initial results are promising. So we've got a good PROMAX alpha and item total correlation. We got a spread of curiosity scores. They're all on the upper end. So it's a scale from 1 to 7, and they're all in the range so far from 5 to 6.5. But we are now rolling this out to a larger sample to investigate further. So if you are interested, get in touch. Right, now I want to talk about the mechanisms driving curiosity, exploration, information seeking, to explain where this comes from. We've already heard several theories, several potential mechanistic explanations in the workshop. I want to offer one too. And that is based on neural network learning. So I want to talk about a neural network model of infant categorization that explores in a curious sense. That's something Katie Toomey and I published 3 years ago. So when we study infant categorization, what we normally do is we put the infant in front of a screen in the lab and show them a sequence of objects, like, for example, a sequence of cats, and then we test them on a sequence, on a pair, a cat that wasn't part of the familiarization sequence and a dog, and we measure if they have preferential looking preference for one of these two items. And in this case, what we will find is that they have a preference for the dog. And from that, we then conclude that they have formed a category of the cats to which this new cat also belongs, but not the dog. So that's the typical way for the last 30 years that we have tested how infants form early perceptual categories. And one, or even longer than 30 years, because one seminal study in this paradigm is by Barbara Younger from the mid-80s already. And she she had animals that animal drawings that differed in 4 features. So they all had a defined leg length, a neck length, a thickness of the tail, and the distance between the ears. And she studied how if infants would group these animals into a category when they were presented one after the other. And the way this was done was that they were familiarized on a random sequence of these animals. And then there were 3 test animals. One was an average that falls into the center of this category. So if infants have formed a category, they should find this not very interesting because it's like the prototype. But the more peripheral items would be more interesting. That would be more at the edge of these categories. So that was the idea. And she found that infants did form a category. 10-month-olds did form a category of these items. So that they look long at the peripheral and at the central item when you show them next to each other at test. Now, Emily Mather and Kim Plunkett asked the question that could be of high relevance, but is normally ignored. Does it matter in which sequence you show the familiarization items before you test on the category formation? And so they designed 2 extreme ways of ordering these items. They were the same items, but they were just shown in a different sequence. In one was a low distance item, then 2 successive items were always very similar to each other. In the high distance sequence, the items were ordered such that 2 successive items are always maximally distant from each other. And what they found was that infants did form a category better when they had experienced this high distance familiarization procedure order. So then they learn best if the stimuli are ordered in this maximally varied sequence. You could say perceptually maximally complex sequence. So first we wanted to replicate this work with an autoencoder, like Dini Marischal has done early work on this, and then later I worked with him to continue this work to use autoencoders as models of infant categorization. So an autoencoder is a neural network that sees an input and has to reproduce this input on the output side. So input and target are the same. And the model can learn this by adjusting the weights. And then we can test it by showing it new items and measuring the error, how far the encoding, the output encoding of the object differs from the input that the model sees. So we can measure the error that a network creates for a specific stimulus, and we can link this to the looking time in an infant study, that when infants look at novel stimuli. And that has been validated quite nicely. That works very well as a model of infant category formation. So we use this now to model these results by Mather and Plunkett to show the 2 sequences to the model, the very similar, the minimum distance sequence and the maximum distance sequence. And then we tested the model on the younger test stimuli. And what we found was replicating the Mather and Plunkett empirical work, that the model that had seen the maximum distance sequence where successive items were very different from each other had a higher error to the peripheral stimuli, meaning it had formed a stronger category than the model that had seen the sequence where each successive item is very similar to the previous one. Okay, so making the stimulus sequence more complex, more variable improves learning. But this was not a curious model. The sequence was predetermined by the experimenter. So we asked, how can we make this model curious? What would happen if the model can choose the next item by itself? So a curious model that actively explores the environment. So for that, we have to answer this mechanistic question: what drives a learner's curiosity? And our answer and assumption is learning progress maximization, so that infants explore the environment in a sense that maximizes their learning at each point in time. So that an infant and the model would choose a stimulus from which the model can learn maximally at this point in time. Now, learning in a model, in a neural network model like this, is given by this by the backpropagation equation. That's a backpropagation model. So the weight change is termed by the difference between the input and the output times 1 minus output. That's just the equation. And learning is maximal when this term is maximized. That means the change of the weights, the learning in the model is maximal when we maximize this term. So what we did was we said, okay, let the model see all the stimuli and then check for each of them which of these would maximize this adaptation. So basically, the model sees the 8 stimuli here, computes input output times 1 minus output, and asks itself from which of these can I learn the most, and then chooses that one to actually learn from it, to really adapt its weights to learn from it. So this is different from previous category learning because before, the adult always chooses the most different stimulus sequence for the learner, or in typical categorization studies, we just randomize that sequence. But that does not take the internal state of the learner into account, of the infant into account. It's just an externally imposed sequence. But now, in this curious model, the learner chooses the stimulus from which it can learn the most. So this, and this choice is a combination between what information is even available in the environment, what can the model choose from, but also in the internal state of the model. What is the prior knowledge of the learner? How ready is the learner to learn from a particular stimulus? And so what we found was that the curious model that chose the objects in this way learned just as well as the model that was given this optimally complex sequence externally. And it learned better, as we see in the graph here, than a model that at each step always chose the most different remaining object, and much better than a model that always chose the next object that the neural network model could encode the worst. So we call this objective novelty. What is the most different stimulus in the environment objectively? And subjective novelty. What is the stimulus that the model can encode worst? So pure novelty seeking did not lead to learning that was as good as this curious model, which wasn't only based on novelty, but also on the internal state of the learner. So curiosity is maximizing learning, therefore leads to learning that's as good as the a priori optimally structured complex environment. But it's a local learning process where a decision is made item by item and not a global a priori structuring of the learning space. Then we looked at what level of complexity does the curious model generate. And again, these were intermediate levels of complexity. All the possible sequences of these 8 items, there were 281 possible sequences. And the models on average chose the 40th most complex one. So intermediate with a trend towards more complex sequences. So the insights that we can take from this model is that curiosity-based learning emerges from a close coupling between the environment, what information is available, the internal state of the learner, the prior knowledge, the readiness to learn, like the zone of proximal development of the learner at that point in time, and the learning mechanism. And the learning mechanism here is in-the-moment learning maximization. And these are critical for real-world curiosity-based learning. Now we've put our heads together with Elena Aldman, Marina Bajdai, Xiaoyun Chen. You might have seen Elena's poster yesterday on this, a theory of curiosity, boredom, exploration, exploitation, and infancy. So the basic assumptions here are that exploration, like in the model I just presented, is driven by in-the-moment learning maximization, that learning about something that is related to what we already know is easier, which we also know from neural network learning. And then distinguishing between exploration and exploitation, we say that when you explore your environment, exploitation is really also exploration, but it's focused exploration. Exploitation is when you explore focused in one part of the environment. Exploration is more broad across a larger environment. And that curiosity is related to the anticipated reward of learning, that learning is rewarding. And therefore, if you maximize learning progress, it is more rewarding. And curiosity is, in a sense, the feeling that accompanies that anticipated reward for learning. If we recap what I said earlier in the talk, the types of curiosity, the diversive curiosity that is meant to keep us from boredom by exploring broadly and perhaps unsystematically, and specific curiosity where we want to answer a specific bit of information and that they are assumed to be qualitatively different. Our theory says they're really two ends of one continuum. So if we imagine an environment here like this, where the infant can learn many different objects, initially there might be diversive curiosity with more or less random exploration. And you might remember this famous video that I think in Azura Jerry's talk featured at the beginning, where the baby rolls around on the floor, playing with all kinds of objects. So that would be that state, and so on. But then it might so happen, so exploration, this broad exploration, is driven by diversive curiosity. But then as the infant explores a particular space of the perceptual environment, there might be another object that's similar to it. And that is therefore easier to learn because the infant already knows something similar to it. So this increase, so learning progress will increase in this part of the environment that is being sampled through accidental exploitation, because the infant just stumbled on an object that is similar to one that has already seen. And then once you start exploring, many more objects occur. So the focus of the learner could then be the attention directed more at objects that are more similar in this space, and there would be deeper exploration in this space of the environment. So continued exploitation until the learning progress decreases. So you don't want to go on forever exploring this space of the environment. Boredom sets in. But this is then specific curiosity, this focused exploration in one part of the environment. Now, when learning progress from this exploitation has decreased, the learner would return to exploration and explore more broadly. But here you already see maybe now birds will be the next area of focused exploitation. I think my sister wants to say my daughter wants to say goodbye. She's going to school. Okay, but I'm giving a talk. So here is the figure from Elena's poster yesterday. So in exploitation, expected learning progress is rewarding. It reinforces further engagement, but the learning progress goes down, and there's a boredom threshold, which would normally lead to disengagement. But as already we discussed earlier in the workshop, I forgot which talk it was, that sometimes you have to engage with information that is really not rewarding. So you have to do something even though it's boring. I thought it was learning kanji characters was the example. And we would think that executive function would help to continue exploration or exploitation in this case, even below the boredom threshold. So this theory unifies diversive and specific curiosity because they are both, well, one is broad exploration, one relates to focused exploration. Therefore, also exploration, exploitation, as emerging from in the moment learning maximization. So that each step the learner wants to investigate that object that affords maximal learning progress. And curiosity is the arousal, as I said, that accompanies the anticipated reward of learning. So the question is then really, is curiosity a mechanism or is it an epiphenomenon of anticipated learning reward? Elena's just started a study now to test this theory. Let's check the time. So this is with Fribles, I think they're called Fribles. So they're objects from different categories, like clearly different categories, but within each category, these objects differ also in their specific features. And this is a case contingent eye tracking paradigm. So there are two houses on the screen, and all the Fribles from one category, they live in this house, and the others live in that house. And when the infant looks at one of them comes out and becomes big on the screen. So we can see how do infants stick to one of these categories, and when do they switch to the other category? And the question can we predict when they switch to the other category based on the similarity relationship of objects that they have seen before, and how often do they switch? So we can also look at individual differences there. So here is the progression, the two houses, the infant fixates one of the Fribles comes out, then attention getter, the two houses again, and then the infant might trigger the other one. And so each infant generates a sequence of these objects from the same or different categories. They're all unique stimuli, even if they look similar, but obviously the two categories differ more than within category. So exploitation, we can say, would be consecutively triggering objects from one category, exploration, switching between the categories, like between here and here, for example. So this is also in early stages. Elena says 13 infants so far, age range 10 to 11 months. And here are for these infants the sequences that they generate. So overall, we see that they often exploit quite a lot. So they stay in one of the categories, then they switch, go back to the original one, for example, here. So of course, we cannot say a lot about this already. It's early days. But we find that there's a good distribution of switch proportions across the infants, normally distributed. Some switch a lot. Most of them switch about every third or fourth category, and also clustering the sequences that the infants generate. We can already see that they seem to cluster in different groups depending on the number of valid triggers, like the length of the sequence that they generate and the switch proportion. So overall, to conclude then, so obviously we'll have more data for this soon. Overall, then, to conclude, infants are curious learners. I think that's undebatable. They explore the environment systematically with a preference for intermediate novelty complexity when they generate sequences, and the brain signature of this special status of intermediate complexity we found in the PB component around 300 milliseconds after stimulus onset. We found that curiosity in infants enhances learning more generally, in contrast to children, teenagers, but like adults. And then that learning maximization is a plausible driver for curiosity-based exploration in infants, both in the computational model and then in the theory that we are developing following that. And of course, that's what we are here for. There are many exciting open questions. And before I completely end, I want to quickly put in an advertisement for our infancy conference in Lancaster, the LiCiD conference that we're running for the 7th time this year in August. We already have 2 confirmed keynote speakers. You might detect some continuity here, Nivi and Sabine. We will send the call for abstracts out soon, so if you can, come and join us there. And with that, I want to thank you very much, and my collaborators, my funders, and our Lancaster Baby Lab team as a whole. Thank you.